our first speaker this morning is Bohm-Jung from Seoul National University. His title is Quantum Distance and the Anomalous Landau Levels of Flat Band. Professor Yang, please start.
Okay, thank you very much for the introduction. Okay, I'm Bohm-Jung from Seoul National University. So first I'd like to thank the organizer, Professor Sang-Jin Shin and also Kun-Young Kim for inviting me to this wonderful workshop. So I'm going to talk about the quantum distance and anomalous Landau levels of flat band. Okay. So let me first acknowledge my collaborator. So the key player of this project is Dr. Junwon Lim at the IBS Center for Correlated Electron System. And also the first principle calculation is done by Dr. Q Kim at Kairi. And also my talk is based on these two recent publications. Let me first explain what is the flat band. As a flat band indicates the dispersion-less electronic band structure, which appears in many lattice Hamiltonian. For instance, this is the Kagome lattice. Here, if we consider the nearest neighbor hopping, we can obtain this band structure. Here we see the flat band, okay, here. So one interesting property of this system is that here the flat band is touching with another parabolic band at the gamma point, okay? Another example is the Lieb lattice shown here. So in this system, if we consider nearest neighbor hopping, here we see this band structure. So in this case, here the flat band is crossing with another Dirac-like edge dispersion at a single point. So in this system, if we slightly modify the hopping amplitude, we get the gap flat band, which is decoupled from the other band structure. So this example shows that we can often see the flat band in many lattice systems, and in some cases the flat band appears as a decoupled isolated flat band, but in some cases actually we see the flat band is crossing with another band at a single point. Okay? So recently actually some flat bands are actually realized in several real compounds, such as the twisted bilayer graphene and also Kagome metal. So in the case of twisted bilayer graphene, depending on this rotation angle between two graphene layers, the band structure, the bandwidth of this state near zero energy actually changes a lot. So in particular, when the rotation angle is around 1 degree, actually we see the emergence of the nearly flat band at the Fermi level. So in the case of Kagome system, like this iron tin, this iron actually make honeycomb lattice. So we can expect this kind of a flat band structure, which is actually measured in experiment in a recent RPS study. So this example shows that now there are materials where the flat band actually realized. So why is this flat band interesting? So traditionally, this system has been considered as a platform to see the strong correlation physics, because in flat band, the bandwidth actually is nearly zero, so the kinetic energy is much smaller than the Coulomb energy. But because of this, actually the interaction effect can be very important. So up to now, several interesting many-body ground state, including ferromagnetism, original crystal formation, and are actually proposed. And recently, in the context of the twisted bilayer graphene, the interplay of the mode physics and superconductivity is another very interesting topic. But in my talk, I'm going to see this flat band from some different angle. Okay, here I'm going to tell you that in flat band, actually, we can observe some anomalous Landau level spectrum, which is also another interesting property of this flat band system. Okay, so in general, actually, the one convenient way of describing the Landau level of metal actually is to use the semi-classical theory, which is based on the Onseger's semi-classical quantization rule. So the relevant equation is actually shown here. Here the S0E basically indicate the K-space area of the closed semi-classical orbit at the energy E. This basically means the Fermi surface area. Also here the gamma indicate the quantum correction arising from Barry phase or magnetic susceptibility, etc. Okay, so let me show you one simple example where how we can apply this actual equation. So here we consider the single parabolic band. Then for given energy E, actually the Fermi surface has a circular shape. Then the corresponding Fermi surface area is simply given by pi kf square. Okay, here kf is Fermi momentum. But since here we have a parabolic dispersion, so here the kf square is proportional to energy. So we have an energy here. Then also by using the fact that here the Barry phase is equal to 0, we can actually immediately see that get this conventional Landau level spectrum with which predict the equally spaced actual Landau level. Okay. So basically in the semi-classical picture theory, the way we understand Landau level spectrum is like this. Without the magnetic field, we have a continuum and energy spectrum. But once you apply the magnetic field, so within some finite interval, this continuum state is simply squeezed to its average energy. Okay, there's a similar squeezing actually happen in every interval, so which give us this equally spaced discrete Landau level. Okay, so in this semi-classical picture, to have a Landau level, we need a finite density of state before you apply the magnetic field. Basically, this semi-classical theory can also be applied to the graphene, Dirac semi-metal such as graphene. So in this system, basically, that we can use the same idea, but the only difference is that here, because of the linear dispersion relation, here the kf square is proportional to E square, and also here we have a pi Barry phase. So if we put this information to this equation, we immediately get the famous Landau level, which is proportional to square root n. Okay? So in this way, the semi-classical theory can successfully explain the Landau level spectrum in any metallic system. But the thing is that if you apply this semi-classical theory to flat band, there's a problem because in flat band, basically every closed loop actually on this flat band can be a semi-classical orbit. So we cannot actually single out the semi-classical orbit since all the closed loop are basically on the same energy. But the one simple way to understand the Landau level of this flat band is actually by starting from this parabolic band and taking the limit of the infinite mass. Okay, basically by flattening this dispersion, we can get the flat band. But the thing is, in the case of parabolic band, we know that the Landau level spacing is basically inversely proportional to mass. This means that if you take this infinite mass limit, this Landau level spacing just becomes 0. So this means that if you apply the magnetic field to the flat band, it just remains invariant. We don't see any Landau level splitting. Okay, but this is what we expect from the semi-classical theory. However, as I mentioned at the beginning, so in many cases, the flat band actually have some band crossing with another parabolic band at a single point. Okay, so for this system, if we naively apply the semi-classical theory, the corresponding Landau level spectrum actually would look like this way. Okay, at first, this actually parabolic band will make the conventional Landau level with the equally spaced actually Landau level structure. Okay, also this flat band actually should not respond to the magnetic field because of the infinite effective mass. So this should actually invariant on the magnetic field. Then we can expect this type of the Landau level spectrum if we naively apply the semi-classical theory. But the question is whether this is correct or not. Okay. The answer is actually the actual Landau level spectrum depends on the singularity which at this crossing point. If the wave function at this crossing point is non-singular, actually actually the actual lambda level spectrum looks like this. So basically the flat band shows the lambda level spreading. So on the other hand, if the wave function at this crossing point is singular, actually here I've shown that the lambda level of the flat band shows a finite spreading, and it appears below the energy of the flat band. So this such a spreading is very unusual because, as I said before, in general, according to semi-classical theory, we can always see the lambda level when there is a finite density of state before we apply the magnetic field. But below this flat band, actually, there's nothing before we apply the magnetic field. But here we see the appearance of the lambda level below this empty region. This is highly unusual, actually, physical phenomena. Okay, this is the outline of my talk. So I'll first explain what is the singular flat band in more detail. And in the second part, I'm going to explain the anomalous lambda level and its relation to the quantum distance. Then actually I conclude my talk. So again, in Kagome lattice, if we consider the nearest neighbor hopping, we get this actually band structure with a flat band. And here the flat band is touching with the parabolic band at the single point, okay? And actually these days, whenever we see such a band degeneracy, we always ask its origin, okay? What protect this degeneracy? Is it protected by symmetry or by some topological region? But actually, interestingly here, this actually band degeneracy is nothing to do with any of this, okay? Actually, this band degeneracy is protected by the fact that here we have a flat band, okay? In that sense, this kind of band structure can be considered as a flatness inverse semi-metal, okay? So let me explain what this means actually in more details. In general, actually the flat band in momentum space basically indicate the localized state in Lie space, okay? So in the case of Kagome lattice, we can find this actually, it is hexagonal state is one example of the localized eigenstate in Lie space, okay? So in this case here, the 1, -1, 1, -1 indicate the wave function amplitude at each side. So we have this finite amplitude only at the 6th side, but outside the wave function amplitude is 0, okay? Such a localized state is called the compact localized state in general, okay? So to have such a compact localized state as an eigenstate, actually two conditions should be satisfied. At first, there should be no leaking of the wave function amplitude when the Hamiltonian is applied. And second, actually this should be, of course, the eigenstate. We can easily check these two conditions by applying Hamiltonian to this eigenstate, to this localized state. And first, actually, if you look at this hopping amplitude to its neighboring side, we can see there should be complete cancellation of the hopping amplitude because of the sign alternation of the wave function of this localized state. So there's no leaking. Also, if you apply this Hamiltonian, we can easily see that this hexagonal state is the eigenstate with energy -2. Okay, so in this figure, the -2 is the energy of this flat band. So basically, this means that this actually contribute a part of this state of this flat band. Yeah. So actually, in our recent work, we showed that for given flat band, we can always find a compact localized state as an eigenstate. In general, we can show this actually. Then, once we find a single compact localized state, by applying the lattice translation, we can fully cover the full lattice structure. Here, actually, I'm assuming the periodic boundary condition, okay? So here, once we find this hexagonal state, by applying the lattice translation, okay, we can fully cover this Lie space lattice. So basically, this means that if the system is composed of the n unit cell, we can also find the n actually compact localized state. But the one important property of this Kagome lattice system is that if we sum all the compact localized state, we have 0. We get 0. The reason is very simple. If you look at this actually yellow side, the wave function amplitude from this hexagon is equal to +1, but the wave function amplitude from this hexagon is equal to -1. So if we add these two wave function, the wave function amplitude this side becomes 0. Okay, and similar cancellation happen at every side. Then this actually give this result. Okay, so this means that among the n compact localized states, only n-1 states are linearly independent because of this actually global constraint. Okay, but if you want to completely span a single flat band, we need n independent localized state. So here the one state is missing. Okay, and this one missing state can be actually provided by the so-called non-contractive loop state. But here, this line state is actually one localized eigenstate with the same energy as the flat band. We can easily see that here we again see the sign alternation, so there's no leaking of the wave function amplitude, and this is also eigenstate with energy -2. But the thing is that if we prepare the system under periodic boundary condition, and actually we can find two actually independent loop states. Okay, basically we can find two different loop states in this system. Then, if we count the total number of localized states, we have n-1 hexagonal state and 2 loop states. So in total, we have n+1 localized state with the same energy. But to span a single flat band, we just need n state. We have overcomplete basis, and this extra one state should be provided by another band, which is degenerate with a flat band. Okay, this basically counting guarantee the presence of the band crossing point here. This is actually a nice picture proposed by this paper by Leon Barnes group a long time ago. But in our recent work, we actually provide a momentum space approach to the same problem. So basically, in our viewpoint, this extra degeneracy at the gamma point is actually encoded in the singularity of the flow wave function. So let me explain what this means in details. So the type binding Hamiltonian describing the Kagome lattice has this form, and the corresponding eigenvector for the flat band is given is like this. So here the CK indicates the normalization factor. So what is interesting here is that at the band crossing point where the K is equal to 0, we see that all the three components become 0 at the same time. So this means that this normalization factor becomes infinite at the band crossing point. But this means that there is some kind of singularity of this eigenvector at the band crossing point. So to see this singularity more clearly, let's look at this eigenstate, the form of the eigenstate, and when you approach this band crossing point. So we take the two different paths to approach this band crossing point and look at the relevant wave function. So we see that depending on the path we approach this crossing point, we have a different eigenvector. So this means that there's actually this continuity of the wave function at this crossing point. Okay, but this is basically the meaning of singularity of the flow wave function, which that I mentioned. So actually, in general, we can show that if the eigenvector of the flat band has a singularity in the Brillouin zone, we can already show that the corresponding compact localized states are incomplete. So because of that, we need to introduce additional loop state, which actually guarantee that this degeneracy. Okay, so this is actually what we have shown recently. So based on this idea, we classify the flat band into two classes. So one is even if the band structure looks the same, basically this flat band can be categorized into two different groups. So one is the non-singular flat band. So in this case, actually, the wave function is analytic even at this crossing point. The other class is actually singular flat band. In this case, there's a discontinuity at this crossing point. Okay, so in this case, actually, the compact localized state form a complete basis On the other, in this case, actually the compact localized states are always incomplete. We need a non-contactive loop state. So another important, interesting difference between these two classes is that in this case, we can open a gap at this crossing point while keeping the flat band flat, okay? On the other, in this case, once you open a gap at the crossing point, this flat band always develops the dispersion. Okay? This is another important difference between these two classes of the flat band. Okay, now let me move on to this lambda level problem once again. So in the case of the non-singular flat band, there's no spreading of the flat band lambda level, just the flat band remains invariant. In the case of singular flat band, we see the finite spreading of the lambda level below the energy of the flat band. Okay. If we label the lambda level in this way, E0, E1, E2, basically we see that the energy of nth lambda level is proportional to 1 over n. This is clearly different from the case of the usual parabolic band, where En is proportional to n. Okay, but this is a very unusual lambda level spectrum. Actually, when you first actually look at this result, actually we try to visualize the singularity actually more easily. Okay, for that, what we did is like this. Since this band structure is basically, this is just a two-band system, we can describe this band structure using the 2x2 matrix Hamiltonian as shown here. Here, sigma x, sigma y, sigma g are 2x2 Pauli matrix. Then using this Hamiltonian, we can define this pseudo spin in a conventional way, as shown here. Then what we did is, we consider the circle enclosing this band touching point, and at each point of the circle, we draw the direction of this pseudo spin. And the result is shown here. Then first, in the case of non-singular flat band, we see that pseudo spin is pointing to the same direction. Okay. Now, on the other, in the case of the singular flat band, the pseudo spin cannot maintain the same direction. We always see some canting of the direction of the pseudo spin, and also depending on the strength of the singularity at the center, sometimes. So this pseudo spin make a full rotation, full 4 pi rotation, and come back to this original point. Okay. So this actually just shows that there is some way to characterize the strength of the singularity at the crossing point. That one way is to measure the maximum canting angle along this circle. So in the case of non-singular flat band, since the pseudo spin is always pointing to the same direction, the canting angle is basically 0. But in this singular flat band, actually the maximum canting angle appears between these two pseudo spins. We have a finite canting angle. And in this case, actually the maximum canting angle is basically a pi. We have a maximum value of the maximum canting angle. And in each case, if you look at the lambda level spectrum, actually it looks like this. In the case of this, okay, it is non-singular flat band. We don't see any spreading of the lambda level. But for this singular flat band, we see the finite spreading of the lambda level. And finally, for this actually singular flat band, we see the large spreading of the lambda level. So this means that the total spreading is somehow proportional to the maximum canting angle. Okay. So actually, we try to find some more mathematical, rigorous way, the beautiful way, to treat this suggested strength of the singularity, and found that basically this singularity at the crossing point can be measured by something called the Hilbert-Schmidt quantum distance. Okay. In general, Hilbert-Schmidt quantum distance is defined in the following way. So here we pick the two momentum k and k prime, and look at the corresponding wave function vk and vk prime. Okay. Then the quantum distance square is given by 1 minus absolute value of the wave function overlap squared. Okay. This is a general definition. Then what this means is like this. If these two wave functions are identical, then since their overlap is equal to 1, then the relevant quantum distance take the minimum value of 0. On the other hand, if these two wave functions are orthogonal, okay, then since the overlap is equal to 0, then this quantum distance take the maximum value of 1. Okay, basically this means that this quantum distance measure the similarity or the difference of these two wave functions. Okay, it shows how similar these two wave functions are. Then basically the strength of the singularity at the crossing point is basically measured by the maximum value of this quantum distance. In fact, there's a one-to-one correspondence between the maximum canting angle of the pseudospin and also the Hilbert-Schmidt quantum distance. We see that as the canting angle increase, the Hilbert-Schmidt quantum distance also increase. Okay? So one of the most important results we obtain in our recent study is like this. So for this singular flat band, we see the finite spreading of the lambda level. Here the delta indicate the total spreading of the lambda level. Then if you take the ratio of this delta over h bar omega c, here the h bar omega c is basically the spacing of the lambda level spacing of this parabolic band. Then this ratio is actually solely determined by this Hilbert-Schmidt quantum distance. For example, here we plot in this figure, here this blue dot indicate the numerically measured lambda level spacing. And here we see all the data points are sitting on a single, this red line. It means there's a single universal function that determines the relation between this ratio and the Hilbert-Schmidt quantum distance. And this basically means that once we measure the spreading of the lambda level in experiment, we can measure the quantum distance between the wave function. Okay, so basically we think this is the first proposal of the method measuring the quantum distance of the wave function in condensed matter system by applying the magnetic field. Okay. So here let me explain how the singularity and also pseudospin canting are related to this spreading of the lambda level. So to see that, let's look at this weakly singular limit with a small small quantum distance where the analytic treatment is possible. So in this limit, basically the Hamiltonian for singular flat band can be obtained by starting from the Hamiltonian for non-singular flat band by adding some small perturbation. Okay. So before you apply the magnetic field, the Hamiltonian for non-singular flat band has this simple form. It is already block diagonal. So in this case, since only the single Pauli matrix is appearing, the corresponding pseudospin is always pointing to the same direction. Very simple. So now if we add a small off-diagonal term, so we can see that we always see the singularity at this crossing point due to this off-diagonal term. Moreover, since these off-diagonal terms are proportional to sigma x and sigma y, once we add this off-diagonal term, actually we immediately see the canting of the pseudospin. So this means that the singularity of the wave function at this point and the pseudospin canting are actually closely related to each other. So moreover, since this additional term appears in the off-diagonal part, it is very natural to expect some kind of a level repulsion between these two diagonal band structure. Okay, so this is actually exactly what's happening in the lambda level spectrum. So if you look at actually this is the effective Hamiltonian describing the coupling between the nth lambda level of the parabolic band and also nth lambda level of the flat band. Okay, here we can clearly see that the off-diagonal term that describes the level repulsion is actually linearly proportional to the Hilbert-Schmidt quantum distance. Okay, that this means that this is the Hilbert-Schmidt quantum distance is exactly the region of this level repulsion, which gives the spreading of the flat band lambda level. Okay. So we confirmed this theory using the various lattice model, including the Kagome lattice and also checkerboard lattice, and both of them shows this singular band crossing. And here we see that this flat band is basically maximally singular flat band.
Bohm-Jung,
Yes.
so why there is an accumulation? Can you say again?
What do you mean by accumulation?
The levels are accumulating.
Levels
Accumulate, not just spreading, but infinitely many levels are accumulating at certain. Can you go just one more slide back?
Yeah.
Right there.
We have a spreading basically. Okay.
Right, and the near zero.
Yes.
Isn't it that is you are indicating accumulation of the energy levels?
Actually, in the continuum Hamiltonian, continuum Hamiltonian always predict the infinite number of lambda level, but the lattice model, in the lattice model, we have a finite number of lambda level, basically. Okay.
Right, but the near zero there looks like an infinitely many.
This is the result because the density is pretty high here and here. So that's why it looks like continuum, but in reality, in lattice system, we have a finite number of lambda level.
No, just I mean even that approximately. So what you are saying is that all these equally leveled lambda levels are somehow, I mean, the accumulated near zero. Is that what is happening?
Yes, because the energy of the lambda level is proportional to 1 over n. Okay.
So what makes that 1 over n accumulation?
This is a result of the level repulsion, actually, that I mentioned. So if there's no singularity at the crossing point, we don't see any splitting of the lambda level. Okay. But once you apply basically many lambda levels are just accumulated at the same zero energy. Now, once you introduce the singularity here, they actually show the spreading. They show the spreading.
So the degeneracy are just splitted. I see.
Yeah.
Okay, thank you very much.
Yeah, so again, this 1 over n dependence of the lambda level actually naturally leads to the log divergence of the orbital susceptibility, which actually provides a new mechanism for diverging orbital susceptibility. Also, we found several materials where this idea can be tested. In particular, in the case of this cyclic graphite, which has this structure, we see almost perfect flat band with a bandwidth about 0.04 MeV, and this is a very good quantitative system where we can observe the singular flat band. So before I conclude my talk, let me briefly mention the geometrical meaning of this result. So in general, the geometrical property of quantum state actually are characterized by something called the quantum geometric tensor. And the quantum geometric tensor is defined by using the definition of this quantum distance that I mentioned before. So in practice, if we consider the two wave functions which are basically nearby in the parameter space, in general, the distance between these two wave functions take this form. Here, the chi alpha beta is called something called the quantum geometric tensor, which describes the geometric structure of the Blow wave function. Then the imaginary part of this quantum geometric tensor is called the Berry curvature, and also its real part is called the quantum matrix. Okay, so this means that Berry curvature and quantum matrix are two actually components that describe the geometric property of the Blow wave function. But up to now, there are many studies about the Berry curvature physics. We know the physics of Berry curvature pretty well. But not many relatively little attention have been paid to the quantum matrix. So we don't have a clear picture of the physics of quantum matrix. Okay, so in this way, actually, we show one clear example where we can clearly measure the quantum matrix in condensed matter system. But I believe that there are many interesting issues or interesting physical property which are related with this quantum metric, which are not actually discovered yet. Okay, now let me conclude my talk. So here I studied this singular flat band, property of singular flat band, and actually showed that by measuring the lambda level spreading of the singular flat band, we can precisely measure the quantum distance of the wave function. Okay, that's it. Yeah, thank you for your attention.
All right, thank you for very interesting talk. So now the session is open to questions. Kiso?
May I have a question?
Yes, please.
Hi, Bohm-Jung. This is Kisok. Yeah.
Yes.
Yeah, great discovery. So I think I didn't understand the origin of singularity at the band touching point, which gives rise to, from the microscopic lattice model, can I see which lattice model gives such singular band touching point between flat band and parabolic or whatever? Can I see from the band, lattice model or from UV itself? So what's the origin of the singularity here?
Yeah, I think maybe the one maybe the convenient way to look at singularity is to look at the eigenvector directly actually. Just a second, please. Yeah, here. So, for example, this is the eigenvector of the flat band for Kagome lattice. So we see that in this system the band crossing is located at the gamma point where the k is equal to 0. And at this point, we see that all the three components of the wave function become 0 at the same time, 0, 0, 0. Then this means that this normalization factor should become infinite, right? To normalize the wave function. But this is actually the signature of this singularity, okay? So for any lattice Hamiltonian, and you derive the eigenvector for the flat band, and when all component of this eigenvector becomes 0, that's the singular point.
Yeah, I understand. Yeah, then so it is not easy, to figure out the existence of the singular point from the lattice model itself. For example, for several cases of topological state, we know just seeing the band structure nowadays, we can distinguish topological or non-topological. So in this case, yeah, I understand your explanation, so clearer. But so just let me compare two lattice models. One is Kagome, and the other is, I don't know, some non-singular band touching point.
Yes.
And so before calculating some eigenvector at the band touching point, near the band touching point, isn't there any some intuitive or whatever way to see?
Yeah, actually that's a very good question. But at first, I think you mentioned topological phase, but here's the thing. So for example, even if the band structure looks the same, suppose that we have a flat band which is touching with the parabolic band at a single point. Even if the band structure looks the same, this flat band can be non-singular. Okay. So to confirm the singularity, we have to look at the wave function. So actually the same thing applies even to the topological material. So for given topological band structure, just looking at the band structure, we cannot say whether it is topological or trivial. We have to look at the wave function, right? Same thing applies to here, okay? So basically this singularity is one way to, it's kind of the interband coupling, like the Berry curvature. So to see actually whether it's trivial or non-trivial, we have to carefully look at the wave function. Okay.
I see. Yeah. Thank you.
Other questions?
One more question. So suppose I try to solve that, Kagome lattice model under magnetic field, in a brute force way. Is it possible? This is non-interacting problem. There is no exact solution, analytic solution in your calculation.
For lattice model?
Yeah, how can you find the 1 over n lambda level? 1 over n behavior for the flat band?
Basically we derived from lattice model. We used a basically continuum Hamiltonian. So near the crossing point, we have a effective continuum Hamiltonian.
I see.
And we have the full energy spectrum.
I see.
Very simple actually. Yeah.
That's good. That's the necessary condition for great discovery. One more question. You mentioned that you proved that any flat band can be, described by compact localized state. So
right.
Can you sketch how to prove it? Generally, you mentioned that. Yeah.
How to prove it?
Yeah, logic. You mentioned that you can assign any compact localized state to the flat band. So for general lattice, So how can you? What is the argument for
that? To me, it's basically the flat in the momentum space. So it basically means the delta function in real space, right? Generally, that's related by Fourier transformation. So to me, it's very natural to see the localized state in real space whenever we have a flat band in momentum space. Okay.
Intuitively, yes, but you mentioned that you prove it. What does it mean? I expected for general lattice, you have some group classification that based on that, if you have flat band, then you find some condition for some block wave function from that flat band condition. So that's what I expected. What does it mean, proof?
Yeah, so basically the logic is by super let me see by taking some linear combination of the blow state, right? Yeah. When you construct for example Barnier state, we take basically the linear combination of the blow state, and see whether the resulting superposition is expression localized or not. So we check the property of this superposition.
I see.
Basically, we can repeat the same thing.
I see.
Yeah. Right.
So previously you mentioned that what is the protection for the band touching point? Why are you laughing?
Yeah.
Oh yeah. Well, yeah. So
So basically, I made the term the flatness inverse semi-metal, right? It means that here this band touching is nothing to do with the symmetry or topology. Okay? This touching is just protected by the fact that we have a flat band. Okay? It's very strange. It's very strange. So this means that once we allow the finite dispersion of the flat band, we can open a gap. But as we impose a constraint that the flat band should be perfectly flat, then there should be the band touching. It's very actually unusual state actually. Yeah.
I see.
It's a kind of new class of the semi-metal. So yeah.
Can you make it such an argument more rigorous, based on some geometric something?
So we prove it. Using the most general form of the effective Hamiltonian, two-band Hamiltonian. We proved that actually.
Yeah, I understand, but that's very simple Hamiltonian, two-band Hamiltonian.
If we expand it up to quadratic order, there are many terms in the Hamiltonian.
Really? I see.
I see. That is in my paper. Yeah.
I see. Okay. Yeah. Thank you.
Yeah, thank you. Yeah.
Look at the definition of the quantum distance. V and V prime, and what these pairs correspond to? So you are measuring between which two states?
The quantum distance is basically a very general concept.
Right.
Basically, we compare two wave. We pick any two wave function. For example,
No,
let's suppose. Yeah.
So you are the I guess the spreading or dispersion delta is proportional to the quantum distance between V and V prime.
Right.
Remind me what was the V and what was the V prime?
These two, so we pick a two arbitrary momentum in the momentum space, and look at the relevant wave function. Okay, Vk and Vk prime are two wave functions at the momentum k and k prime. Okay, then we measure the distance between these two wave functions. Okay. Basically, what you found is that the lambda level spreading is determined by the maximum value of the quantum distance. It means that to determine the maximum quantum distance, you have to compare the distance between every pair or every possible pair of the wave function in the 2D momentum space. It's a very difficult job, but yeah.
You need to look at all the points at the momentum space.
Yeah, for every pair, but yeah.
The spreading.
Right.
So quite a non-local object, I see.
Yeah.
I see.
One short question. So there are many, studies in quantum information theory for example, fidelity or something, related concept.
Right.
So so what's the difference? So can you give me some examples? So you can find a way. How to find such quantum geometric distance between the wave function or whatever. But from the band structure itself, it's quite new and interesting. But so in quantum information physics, they directly there is no way to measure fidelity or.
Oh yeah, that's also a very good question. So can I share this screen? Oh yeah, okay. Yeah. Oh yeah, sorry.
Yeah, you can share only your screen instead of your face.
Yeah, let me show you one. Yeah, but this maybe. Sorry. Yeah, as Kisok mentioned, okay. So basically, the quantum distance is closely related to the concept of fidelity. Okay, fidelity basically means the definition of fidelity is like this. So we take overlap between these two wave functions and take the absolute value. This is basically the fidelity. If we compare it with the dispersion, the definition of the quantum distance, basically the quantum distance between these two wave functions is just 1 minus fidelity square. Okay. Then so there's actually one-to-one correspondence between the quantum distance and fidelity. Then the question is, as Kisok mentioned, so in the quantum information theory, we often talk about fidelity. It can be measured. Okay, but the thing is that the interesting point about our study is that we measure this quantum distance between the Blow wave function. That's the difference. In the usual quantum computation, basically, if we can prepare, for example, quantum dot, and each quantum dot we can prepare the one quantum state. Then by considering two quantum dot, we can define their relative distance. Okay, by measuring their, for example, pseudo spin direction. Okay. that kind of measurement can be done, of course, but measuring the quantum distance between two flow states is actually non-trivial.
I see. Yeah, I see. Thank you.
Can I ask a question?
Yes, yes.
Thank you for your nice talk. I just wonder, I can apply this idea to partially flat band.
Yeah,
Is it only valid in perfect flat band?
Yeah, that's also a very good question. So let me again show you. We got a lot of questions from the library about that point. So as you mentioned, in layer system, actually, we cannot have a perfect flat band, okay? But of course, I show you some example where we can see the almost nearly flat band in this system.
Yes.
But in reality, actually, we always have to take into account, for example, second neighbor hopping, right? Also spin-orbit coupling, okay? So once you introduce such a perturbation, we always see the small dispersion of the flat band, okay? For example,
I see.
in this material, we always see some small dispersion. But the thing is that this second neighbor hopping and or spin-orbit coupling can be treated by using the simple perturbation theory, okay? In our paper, we show that how this quantum distance can be extracted when we include the spin-orbit coupling and also second neighbor hopping. But there is a systematic way to improve these computations, and there's no problem.
I see.
Yeah.
I have one more question. Is this idea only valid in 2 dimensions?
At the moment, we only consider, but some concept can be generalized to even to 3 dimensions. For example, the distinction between the singular and non-singular flat band, and some property actually I mentioned in the second part of my talk. But here, for example, this property can be applied even to 3D in general. So.
I see. Thank you.
Yeah, thank you.
So again, Bohm-Jung,
Yeah.
Fixed in this quantum distance. So when you measure, the quantum distance by maximum separation over arbitrarily 2 momentum point.
Yes.
So what intuitively that measure in terms of this, the crossing between the flat band and this non-flat band.
Yeah. Could you? Sorry, I don't understand the question.
So, what is actually the measure of the quantum distance in terms of this singular meeting of these 2 band crossing, this flat band and non-flat band?
Oh yeah. So what we propose is this quantum distance, this maximum quantum distance is somehow this is a measure of the strength of the singularity. That's what we propose.
Singularity.
Yeah, the strength of the singularity. I mean, as I've shown, so even if the band structure looks the same, depending on the strength of singularity, the canting angle of slow spin are actually different. Okay. In some case, we see the small canting angle. In some case, we see a very big canting angle. Okay.
So you actually introduced 2 things. It's one thing is a periphase as antisymmetric part.
Very curvature.
Quantum, yeah, very curvature, yes. And the other one is the symmetric part, which is metric.
Right.
Are there any relation between these 2? That is, if you know one, you know the other, or they are completely?
There's some relation, which I don't remember now, but if we take some kind of integral of the curvature, somehow it's related with some integral of the metric. There's some relation. but that yeah, if you take some kind of integral form, I mean, there's a particular form that relate these two, but they are not actually the same thing. That they are different objects. But if you take some integral, for example, over the 2D momentum space, that we can find some relation between them actually. Yeah.
Because the singularity, I thought that is measured in terms of the Berry curvature.
Actually no, because the reason is actually this is the thing. So in general, to understand the geometric property of the wave function, we have to take into account both Berry curvature and quantum metric. Okay, but in many cases, somehow it seems that Berry curvature dominate the physics. Okay, it's difficult to see the physics of quantum metric. Then the trick I use is basically from the beginning, I made the Berry curvature become 0. So in the model Hamiltonian I study, Berry curvature is always 0. We don't have Berry curvature. So all the interband effects are purely coming from the metric. Okay. So one reason why I studied flat band is in many flat band, Berry curvature is exactly 0, always 0.
But I guess that you are not just looking at flat band, but the crossing of a flat band and something else, right?
Yeah, so this crossing is stable only when the Berry curvature equals 0. Yeah.
So anyway, you are not just looking at the property of the flat band itself, right?
I'm focusing on the flat band because in the flat band system, we can here the Berry curvature effect can be minimized and quantum metric effect can be maximized. Okay.
No, I was asking without crossing between the flat band and some other band, is there any singularity? If you have flat band, that's the question.
So no, without the band crossing, there's no singularity.
Right.
No singularity. But
so
the thing is
of the flat band, right?
Right.
Right.
But the thing is that the gapped flat band, suppose that there's no crossing and we have a single isolated flat band, then the Chern number of the flat band should be always 0. We can prove that, right? So it means that Berry curvature effect should be minimized, right? Somehow, anyway, so in general, flat band system is very good system to study quantum metric. Yeah. That's what I want to say. Yeah.
Thank you.
Thank you. Yeah.
Any more questions?
Yeah, but nearly flat band can have non-zero Chern number.
Yeah, that's a nearly flat band.
Yeah. So in the case of I mean, in connection with the previous question, so suppose nearly flat band with non-zero Chern number and we do some touching.
No band touching. No band touching.
In that case, band touching is not possible.
Yes.
How can I understand it?
Yeah, because for example, in graphene, here the Dirac point is stable because of the Berry curvature is always 0, right? Away from the Dirac point.
Right. Yeah.
So to protect such a Dirac point, the Berry curvature should be always 0 in K space, right?
I see.
The same thing. Yeah, that's the same thing applies to this singular flat band. Yeah.
I see.
Actually, that's the key physics actually in this problem. Actually, that's the key.
I see.
Yeah.
I see. Okay. Thank you.
Right. If no more question, let's thank Bohm-Jung for introducing very interesting example.
Thank you very much. Thank you very much.